Alright everybody, welcome to the first video on the 22 Circles math channel. So this is a new channel that I've created for certain topics that I feel don't really belong on my main channel, 20 Circles. So today we're going to get started with something fun. It's called, as you can see by the title, we're going to be starting with coloring proofs, which you might also hear it called parity arguments, because a lot of times we're going to be using the concept of parity. So we're going to start off with just some basic theory and introduction to what we're going to be doing tonight. And this stuff might be a little bit boring, but just bear with me. Once we get through this, the examples will be much more fun, and especially when you see it in action. But to get there, we will first have to go through some dull, dry theory. So let's just get that out of the way. So in coloring proofs, our goal is to partition a set into a finite number of subsets by coloring each element of a subset by the same color. So that might not mean much right now, but when you see it again through the examples, it should hopefully make more sense. So after this video, after seeing all the examples, I would probably come back to this first page. So the way I like to approach any coloring type of problem is to imagine that my problem is contained in this sort of box shape, right? Well, it doesn't have to be a box, but basically some sort of shape, right? Some sort of boundary. And then the shape is actually divided into certain sections. So in this example right here, we are divided black and white. So this would be the type of problem. So this would be an example of a coloring problem with two colors. In this example here, we have four colors: black, white, red, blue. So this would be an example of a coloring problem involving four colors. And similarly, this one over here involves three colors: blue, red, and green. So that's just how I like to think about these problems. And tonight, I can tell you right now, we're mainly going to be working with problems involving two colors or three colors. We may get the occasional four-color problem, but it's not as common as the others. So in these coloring type of problems, we are mainly concerned with the big question, that being either the possibility or the impossibility of certain tilings. And I can tell you right now that tonight we're mainly concerned with showing the impossibility of something just because it's slightly more interesting. And over here, throughout this document, you're going to see some icons. So over here, I have a little light bulb, and that basically just means like a useful, friendly tip that I want you to keep in the back of your mind, because it should help you with these problems. So the first tip we have right here is that parity and colors, when they're used together, it is a very powerful tool. So just keep that in the back of your mind and recall that parity basically just means the evenness or oddness of a number. So yeah, we're going to be using that a lot today. And then moving on to the next icon, I got this little thinking face emoji, and basically that just means the method of attack, right? Sort of like the strategy that we're going to be using. So today's method for coloring problems is as follows. So the basic process for showing that something is impossible is to first assume it is possible. That's key. We're going to first assume it is possible, break things up into colors, use basic facts about numbers, that's the parity that I was talking about earlier, and obtain a contradiction. And if this sounds familiar, well, this, my friends, is called proof by contradiction. So I'm assuming you have some background of what proof by contradiction is. I'm not going to be going over that in this video, but I will make a separate video on that possibly later. So yes, proof by contradiction is the main proof method that goes hand in hand with coloring. So with all of that out of the way, guess what? We can go into the exciting stuff. So let's jump right into some problems. Quick disclaimer, the first two problems that we're going to see are concerned with chessboards. But don't worry, you don't have to be a chess player to actually solve these. Now typically we will divide the chessboard into two groups, black squares and white squares, and this is very intuitive because if you actually see a physical chessboard yourself, it's already divided into these color squares. So it sort of makes sense to think of the problem through the lens of two colors. So yeah, let's get into some problems because as before, the method that we explained over here might sound a little lofty, abstract, and just like you're probably just like, what? That doesn't really make sense. I don't really get it. Didn't understand anything. That's totally okay. I think when you see it in action with some problems, you'll know exactly what I'm talking about. So let's not waste any more time and let's get into it with your first problem. So as always, I encourage you to just pause the video and just try the problem out yourself first. Have fun with it. But today's first problem is this. So question 1. Is it possible to move the knight, that's this guy, from a comma 1 over here, this bottom left square, to h comma 8, top right square, and visit every square exactly once? So that's once and only once. And for your information, an 8x8 chessboard has 64 squares. And if you're a little confused on how the knight moves, I've written it here. This is how the knight moves. We first go 2 squares in one direction, and then 1 square at right angles to the first direction. So if we started, let's say here, we're going to go 2 squares, let's say 1, 2, turn and go up right at this right angle. So that could be a move. We could also go 2 squares here, turn at a right angle, and end up on this square. So that's another possible knight move. Or we don't have to go 2 squares first and then turn. What we can do is actually go 1 square, turn, and then go 2 squares. But as you can see, with this move, we basically just end up at the same place as that maneuver. So it doesn't really matter whether it's like this or like this. Basically, the knight just moves in a very L shape. So I encourage you to just play around with this problem at first, even if you don't know the answer and you might not know exactly how to use the coloring strategy that I mentioned at the start. Just play around with the problem. Whether you have a physical chessboard or if you don't, you can even just draw an 8x8 grid if you want. You can like draw an 8x8 grid on a piece of paper and just like start moving the knight around like crazy and see if you can answer the question. I'm going to guess that, you know, after playing around with this problem for a bit, you were probably not successful. So in other words, you could not do what the problem asked you to. You could not go from here to here with the knight and visit every square exactly once. But How can I be so confident about that? So yes, here's the answer. The answer is actually no. I'm gonna do a little box around it, like so. So no, it is not possible to move the knight from a,1 to h,8 and visit every square exactly once. But why, right? Because that's the more important question. Why is it not possible? How can we be certain 100% of the time that it's just not possible? And to answer this question, we need to think about how this pesky, very pesky little knight moves, because there's a very important fact about how the knight moves from square to square, and it is as follows. I'm sure if you've played around with it, you might notice something interesting about the color of the square that the knight is on after each move. So the knight, the horsey, always changes color after each move. So in other words, it moves from a black square to white and vice versa after each move. So in our example, if the knight start here on this black square, after a move, it's on a white square. Doesn't really matter which one, but the important fact is it's on a white square. And then from a white square, whenever it has to make a move, whether it's this, or this, or this, or this, we notice that after a move, it will be on a black square. So this is just, the colors, right, sort of coming together. We're thinking in terms of white squares and black squares. That's going to be super important. I want you to remember that concept for all problems that we do in this video. Always try to think in terms of colors, or like breaking the problem into groups, different groups. So what I'm going to do is I've actually prepared another page, because I'm going to make a handy little chart, just a little a chart. And on the left side, I think I will put move, and on the right side, I'll put color of square. So what do I mean by this? Well, if we start on A1, what I mean is after move number 1, we will be on a white square. So that's exactly what I mean by this. So after move 1, the color of the square that we're on is white. Okay. And then move number 2 will take us, if we're on a white square now, let's say this one. Doesn't really matter which black square it is, but the point is, after move number 2, we will be on a black square now. After move 3, we will be on a white square. Move 4 will be a black square, and I think you sort of see this pattern that repeats, right? So we can keep going, dot, 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 all the way to the end. But what is the end? What is the final move? Would it be, well, we're told that there's 64 squares, but does that mean that the final move is going to be move number 64? No, not so. It will not be move number 64, because we already started on this square. So this square has already been used up. So really we have the rest of the board. So that's 63 moves, not 64. And on this final move number 63, well, let's see. It looks like after every odd numbered move, we should be on a white square, right? 1 white, 3 white, 5 white, so on and so forth. So since 63 is odd, after 63 moves from A1, we will be on a white square. But if we look up, dun 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 dun, is h comma 8 a white square? No, it is not. That is a black square. So we see where the contradiction is. Based on the simple fact about the knight going from white square to black square, after 63 moves, the knight should theoretically be on a white square. But as given in the problem, h comma 8 is not white. So that is where the contradiction comes from, and that is why it is not possible. So let's just write that out. Spell that out in a nice solution. So from a comma 1, and let's just put in brackets a black square. After these many moves, the knight should be on a black square. Not a black square, sorry. It should be on a white square. See, I'm getting confused, but hopefully you caught that mistake before I did. Anyways, after 63 moves, the knight should be on a white square, but h comma 8 is black. This is not good, and this is where our contradiction occurs. Great. Let's move on to question number 2, which is a very popular problem. You may have heard about this, but if you haven't, well, take a look. It is dubbed the mutilated chessboard, because this time it's not a regular chessboard. Something weird has been done to it. Let's read. Take an 8x8 chessboard, so standard chessboard, right? But this time we are going to cut, so chop off 2 diagonally opposite corners. And it doesn't matter which corners. I've just selected these 2, but you can chop off these 2 if you want. The question asks, in how many ways can we cover the 62 squares? So there's 62 squares now, remember, 2 are chopped off, of the mutilated chessboard with 31 dominoes. And dominoes measure 2 by 1. So just ignore these numbers over here. Those don't really matter. I just chose a random domino icon. The important thing is the measurement of the domino basically just covers like this, 2 squares. So we have 31 dominoes, and how many ways can we tile it, right? Can we tile this funky chessboard, this mutilated chessboard with these 31 dominoes? So, as usual, I'll let you have a minute to think about this problem, play around with it for a bit, and then come back. And just as a little fun fact over here, an 8x8 chessboard can be covered by 2x1 dominoes in this many ways. So this was found, and we're not going to prove in this video because it's actually a lot harder to prove this than it is to answer this question. Believe it or not, our question is actually much simpler than this. But yeah, that's just a fun little thing to think about. Anyways, let's focus on the original problem. So I said earlier today that we were mainly concerned with showing the impossibility of something because it's much more interesting. So in case you haven't figured it out by now, we got a hint, hint, wink, wink, nudge, nudge. I'm going to guess you weren't successful at tiling this chessboard with 31 dominoes, and I can say that pretty confidently. You know why? Because here is our answer. There is no way to cover the chessboard. Absolutely no way. And if you did find a way, well, then you're wrong. It is 100% impossible. So to answer the question, how many ways, it would actually be, no way, or I'll accept also 0 ways, right? But as usual, the more important question is why? Why is it impossible? And just like the previous problem, it's useful to think about the domino and colors of the chessboard. So the good thing about chessboard is they make it pretty obvious how many colors they want you to think in terms of black and white. So that's what we're going to do. So let's take a look at this domino. Whenever it goes on the board, what do we notice about it? What do we notice about it? You can't be diagonal. That doesn't work. Just like this, you're the horizontal or your vertical. There's an important fact that remains true for every domino. It doesn't really matter which way it is. Doesn't matter which domino it is, doesn't matter which way it's oriented, doesn't matter where it's positioned. The important fact, and hopefully I made it very clear by showing many examples, but basically, each domino covers exactly, let's write that, I like that word, exactly one black and one white square. So if I just drew a domino really quick, each domino would cover one black, so let's just symbolize it like this, and one white. Okay, so if each domino covers exactly one black and one white square, that means 31 dominoes. 31 dominoes, remember, we're given 31 dominoes in the problem. 31 dominoes should theoretically cover 31 black squares and 31 white squares. Right? We've looked at each individual domino covers one black square and one white square. Exactly. So if we have 31 copies of these, then it should cover 31 black and 31 white. But do we have that in this problem? Now there's a very easy way to count how many black squares we have in this problem. So we know an 8x8 regular chessboard has 64 squares, 32 black and 32 white. But if we're chopping off 2 black, that means we have 30 black squares in this mutilated chessboard and 32 white. And I chose these two corners, but if it was these two corners instead, we would have 32 black squares and 30 white. It doesn't really matter which one you choose. The point is you don't have 31 black and 31 white. So let's spell that out formally in a solution. This chessboard has 30, and I'm going to be a bit more general here, so that way it covers both cases, whether we chopped off like these two corners that I chose or these two corners. The point is, this chessboard has 30 squares of one color. Don't really like that. 32 squares of the other color. So therefore, a successful covering of the board does not exist. So I hope we're getting used to this. That's the first two problems out of the way, and those involve chessboards. So now let's go beyond chessboards. But actually, quick disclaimer, I just want to say, even though we're going to be moving away from chessboards, I still want you to understand the concepts and the techniques that we used for these chessboard problems, because it's going to be very useful for future problems to always think, always ask yourself, like, what are my colors, right? And what facts can I derive from this color, right? For instance, this is the important part of the solution, this part right here. So just always keep that in the back of your mind. Let's keep going. Now, in coloring problems, there's often a very specific type of problem called tiling problems. So these ones it's still like a chessboard, but just there's a little bit more going on. So as usual, I have our little buddy, our thinking face emoji, to remind us of our method. And it's basically the same method as the chessboard. So we're going to assign a specific color to each square on a board and show that the tiles cannot satisfy constraints set by the coloring. Of course, if that sounded, very abstract, or you don't know what's going on, don't worry. The problems will hopefully make it clear. So for all of the problems that follow, I'm just going to get this out of the way right now. So from now on, whenever we use the word straight tetramino, we're referring to something like this, right? Because it's just in like a little straight line over here. T tetramino. This is called a T tetramino, self-explanatory, shaped like a T. Square tetramino, again, square shape. L tetramino, kind of like a long L like this, right? And then, as usual, you always have one weirdo in every group, so this is skew. Okay? Let's get into it. Let's do some fun stuff with these five guys. Okay. Anyways, let's get into it. So your first question is it possible to form a rectangle with the 5 tetraminos, one of each? So using one straight, one T, one square, one L, one skew, can you make a rectangle? And I left the sticky note here to remind you, have fun with the problem first. So always experiment. So if I were at home, I would maybe, I could draw these out, maybe cut them up, right? Cut them up around here, and then maybe try to orient them and turn them around, flip them, rotate them, reflect them, however I want to, and just try my best to make a rectangle. So I'm going to let you go ahead and do that. So I don't know if you've noticed a certain theme or pattern about all the problems tonight, but I'm going to guess that you were not successful. And why do I say that? Well, in case you haven't figured it out by now, it is not possible. The more important question is, why is it not possible? Now, I'm actually going to fast forward through this part, but I'm going to show you how I would maybe try to experiment with this. Right, so in case you didn't know what the question was asking, you didn't understand what it was asking you to do, I figured I may as well show you, right? Let's not skip this stuff. So basically they're asking, we take these tetraminos, and you're going to have to bear with me because they're not exactly the same size, but hopefully it should be good enough. But basically, if we take these 5 tetraminos and, we can rearrange them many different ways. if we take them, can we make a rectangle with them? So this is a pretty sloppy example, but basically I was trying to make a shape sort of like this, but as you can see, obviously that didn't work out. We have so many missing squares. I'm sure you probably could have done a better job than me, but regardless, we can see that this was not possible because there are a lot of missing squares. And since I already gave the answer, it is not possible. Let's try and figure out why. So the whole reason I made us do the chessboard problems first is because thinking in terms of the chessboard doesn't exactly go away. It has many applications, even for a problem like this. What do I mean? Well, any rectangle, I'm going to make a bold claim here, so bear with me. Any rectangle with 20 squares can be converted, to a chessboard. And you're probably asking so many questions like, what is this converted to a chessboard, and where is this 20 squares coming from? Well, I don't know if you noticed, but we have 4 squares here, 4 squares here, 4 squares here, 4 squares, 4 squares. That's 20 squares in total that we have to use up. So basically, we are trying to use what we already know. So any rectangle with 20 squares can be converted to a chessboard, and it doesn't really matter how it looks like. For example, let's say we have something like this. Okay? Say I have this sort of long rectangle, right? So it doesn't have to be this kind of rectangle, but in this specific example that I'm showing, I've chosen a 2x10 rectangle, right? You can also choose a 4x5 rectangle, doesn't matter. As long as you're using up 20 squares, it should be fine. The important thing is that this rectangle can now be viewed as a chessboard because we can just simply color it like this. And the beautiful thing about this is that this means that we have 10 black squares and 10 white squares. And this works for any rectangle, even if it was a 4x5 rectangle. If you color it like a chessboard, you're going to have 10 black squares and 10 white squares. And I encourage you to try and do that on your own as well. So why did I make us do this? What is so important about this, right? Doesn't really seem like we're going anywhere at the moment until I do this. I think it's time to make another chart. So I'm just going to do that really quickly. I'm going to speed this portion of the video up. Okay, and we are back. So I just went ahead and made this chart. But why? What does this chart mean? Well, over here, so I've put each tetramino in its own column. And then over here, this means white squares and this means black squares. So basically, we're just going to be counting. So on a chessboard, the fun fact about a straight tetramino is no matter how you position it, it will always cover 2 white squares and 2 black squares. So you can imagine, say in our example over here, if we put the straight tetramino here, it would cover 2 white and 2 black. Maybe if we put it here, it still covers 2 white and 2 black. So that's the first thing to note about the straight tetramino. It's the same story for the square tetramino, the L tetramino, and the skew tetramino. And you can try this out for yourself. You'll see it will always cover 2 white squares and 2 black squares for these 4 tetraminos. But the interesting thing is the T tetramino. So there's a reason why we left it empty, and that's because it's a strange one. And we can even see here, even if we just position, let's say, a T tetramino like this, we can see it's using up 3 squares of one color and 3 squares of another. So, without loss of generality, it doesn't really matter. Let's just say it's like this. In this case, the T tetramino would be covering 3 black squares and only 1 white square. And now we see what the problem is when we total everything up by row this way. We will get a total of 9 white squares and a total of 11 black squares. But this directly contradicts the fact that the chessboard has 10 black and 10 white squares that need to be used up. And this is the power of this coloring proof. It's very elegant, quirky, and very cute, I would say, and it greatly simplifies problems, and it would honestly be kind of hard to solve it without this technique, right? So this is amazing because we have found that it is impossible to make a rectangle. No matter how much we flip, rotate, or reflect these 5 tetraminos, no matter what we do with them, we can, turn them around, rotate them, reflect them, doesn't make a difference. It is impossible to make a rectangle. And we can spell it out. The main problem is actually the T tetramino. Because it always covers 3 squares of one color and 1 square of another. So I'm just writing it out like this, just spelling it out. Or 3 white and, let's be consistent, and 1 black square. In the chart above, I used the example of the T tetramino that covers it like this, but it didn't have to be like that, right? It could have been the other way around as well. So what I mean by that is over here. So the T covers either 3 black and 1 white. That would be the one I showed over here, or it covers 3 white and 1 black. So that would be like this. So above 3 white and 1 black would be this one, right? Over there. Anyways, so it doesn't really matter Which one? It just doesn't add up mathematically. Beautiful. Let's go on to the next problem. Guess we got a bigger board now. Okay. Prove a 10 by 10 board cannot be covered by 25 T-tetraminos. Wow, so it seems like the T-tetramino really is the weird one, right? Not the skew. This T-tetramino causing a lot of problems for us. So I'm going to be going through this one a little bit quicker now that we are more familiar with the technique that we're trying to use today. So we have a 10 by 10 board, and I think it's more useful to view this as a 10 by 10 chessboard. So we got alternating black and white, right? So this would be black, 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 all throughout the board. So that means we would have 50 black and 50 white. Let's just keep that in the back of our mind. Very important fact. And then we're going to recall that a T-tetramino, the weird one, either covers 1 white and 3 black, or, sorry, let me just fix that, or 3 white and 1 black squares. So that would be these two examples here. Let's just put that there. Now, because this 10 by 10 board is even, it has an even number of squares. 100 squares is even. But these are odd. That means we're going to have to put them together so that we can finally get an even number of white and black squares. Right? So if we put these two together, we get 4 white and 4 black squares. So we have an even number. Great. Now you can imagine, let's say the problem is here. Let's say I had 12 copies of this. Let's say I had 12 copies of this. And we're going to tally it up. If I had 12 copies of this tetramino, that means I would have 36 black squares and 12 white. And I apologize for writing the 2's differently. I don't know why I do that. Anyways, if we had 12 tetraminos like this, that would leave 12 black and 36 white. So far we have used up 48 black squares and 48 white squares, but, and there's a reason why I said 12, and that's because we are given that we have 25 T-tetraminos. So how many T-tetraminos have we used up so far? Well, we've used up 12 here, 12 here. That means so far we've used up 24 T-tetraminos. Now, we need one more. And the thing is, it doesn't matter whether we choose to use this one or this one. I hope you see the problem. Let's say we tried to use this one. So this is our 25th tetramino. So if we use this one, let's just make it clear. Tetramino number 25. Again, I'm running the 2 differently. Wow. Okay, tetramino number 25. If we go through a running total, so we're going to this time add this bad boy. Now, guess what? Now we have used up 51 black squares and 49 white squares. And if we did it the other way around, it doesn't have to be this one. Let's say we use this one, then we would have 51 white squares and 49 black squares. Doesn't really matter which one you use. The point is 51 of one color and 49 of another is not what we want. We want 50 of each. So, therefore, let's spell that out. This is a contradiction. So 25 T tetraminos will use up 51 squares of one color and 49 squares of another color. And I'm sorry, I'm writing really fast, so hopefully it's not too messy. Okay, so this is where our contradiction is. So I hope you see it really is the same technique used multiple times. I hope you can see we didn't do anything crazy different from the previous problems, but I'm sort of tricking you because the next one might be a little bit different. Okay, again, this time we're given this 10 by 10 board, so same measurements, cannot be covered by 25 straight tetraminos. Interesting, I thought the straight tetraminos were always working up until this point, but not anymore. Why? Let's figure it out. So I'm first going to approach this problem in the same way that we've always done it before. And if we think of this entire chessboard as black and white, well then, if this entire chessboard is black and white, right, then that means we have 50 black and 50 white squares. And 25 straight tetraminos, well, wouldn't that use up 50 black squares and 50 white squares mathematically, right? Because a straight tetramino looks like this. And we know that the chessboard is colored something like this, alternating black and white. So if we have 25 copies of these, well then it should work out, right? We should get 50 black and 50 white. This is awkward, right? So what happened? We know this can't be right because the question literally says it's not possible. So mathematically, it's making sense, at least we would think. But the question says it's impossible, which means we must be wrong because the question is not wrong. Don't try to argue with the question. So, this is our first problem where we're going to have to do something different. Now, what can we do differently? Well, if you recall back at the start, I said sometimes we might need to use more colors. 3 colors, 4 colors, right? Up until this point, we've just been looking at things in black and white. So that's 2 colors. But now I think it's time we up the amount of colors we're using. And why would we think to do this? Well, because our regular strategy is clearly not working. So whenever you have to think of doing something different in these coloring problems, try to think of maybe increasing the number of colors. So I'm actually going to take this chessboard and I'm going to color it in a very, very cool way. So I'm just going to speed up this process. Just sit back and watch and be amazed. Okay, so I am back, and I have just filled this entire board. I've colored it in a different way. So as you can see, I'm using up 4 numbers. That is 0, 1, 2, and 3. So basically I've colored this board with 4 different colors. And I know it might be a little confusing because 0, 1, 2, and 3 are numbers, but in this example, I just want you to view them as colors. I think it was just a lot easier to work with than like 4 actual colors like blue, red, green, and white. And just writing out the letters, it's just easier to write out these numbers. So we're going to be using these numbers. So we have 4 colors. The colors, quote unquote colors, are 0, 1, 2, and 3. Now, why would I think to introduce 4 colors? Well, if we go back, I can never make a rectangle sometimes. If we go back to how a straight tetramino looks like, notice whenever we place this straight tetramino onto the board now, whether it's here or like here, or this corner here, or maybe even here at the bottom, and the last one maybe like this, no matter how we position it, no matter how we orient it, it will always cover one of each color. Right? So we will always use up one of each 0, 1, 2, and 3. What does this mean? Well, then this means, theoretically, again, hypothetically, 25 straight tetraminos should cover 25 squares of each color. So if I spell that out, that would be, we need to use up 25 zeros, 25 ones, we need to use up 25 twos, and we need to use up 25 threes, because there's 25 copies of these. But the cool thing about this coloring going diagonally is that if you actually count how many ones there are on this board, there are not 25 ones. Wow. So how many are there? There are 26 squares. So that's why this is not going to work. That's our contradiction. What happened to the T? That's our contradiction. And sorry, I don't know why I did not write this very important fact. I just said it out loud, but I didn't actually write it. So I'm gonna go ahead and do that right now, actually, because this is the important part as well. So I'm just gonna speed through this. I already talked about this, but I want to actually like spell it out. So there we go. I've included this very important step because this is a very key component to the solution. So I want to actually spell it out. No matter how we place a straight tetramino on this board, it always covers 1 square of each color. So that's the solution for this problem. And a point I want to emphasize is, what have we learned? Well, we got a new technique, actually. So let's write that out, because we always like adding things to our toolbox, right? We like to collect techniques so that when we see many different types of problems, we have different methods of attack. You don't want to just be fixated on looking at the problem in one way. So sometimes you're probably going to have to change your perspective and increase, so it's more like, I guess, two new techniques, but anyways, increase the number, let's be consistent, of colors. So we got a new technique here, and I'm going to go ahead and box it. Yes, there we go. So I say change our perspective because that's exactly what we had to do in this problem. Instead of coloring things as just black and white in a horizontal fashion, this time this coloring, this is an example of a problem where you actually have to color diagonally. So that's what I mean by changing our perspective. Maybe we'll have to tilt our head a little bit too and increase the number of colors. So again, not just working with black and white, now we have 4 colors. Amazing. Okay, and I think for now this is a good place to stop for the night. I will continue with the next problem tomorrow night, so I will see you guys there. But I hope you had fun tonight. It was, I'd say, very productive. 5 problems. The 5th one used a new technique. And just as a little teaser for problem number 6, maybe you can try this one on your own. Ooh, it's getting pretty tricky. And we are back with question number 6. So question number 6 says, each element of a 25 by 25 matrix is either +1 or -1. Let AI be the product of all elements of the ith row. So remember, I is just a variable, and bj be the product of all elements of the jth column. So we have another variable j. Prove that this entire sum is not equal to 0. Okay, so this seems like a pretty intimidating problem, right? Because of this large number, 25 by 25. That's 625 squares. So that's going to get pretty crazy. So that's why I've given us a small handy note here to work with small numbers first. So that's exactly what we're going to do. So instead of a 25 by 25 matrix, let's just try to look at something smaller, like a 3 by 3. And the reason we go for small numbers first is because they're just easier to work with, and a lot of times when you study the small cases and you look at them in depth, you can get some insight on how to solve the bigger problem. So let's say we have just, can never draw these squares, okay? Like never recognizes it. Okay, here we go. So let's say we have just nice small 3 by 3 matrix, which I'm just going to, represent with this little grid. So it might not be perfectly straight, but hopefully that's good enough. And let's just play around with some examples. So let's say we just go for, remember, every element is either +1 or -1. So let's just fill this up. And maybe, heck, let's just, throw some minus signs in there. And we're going to do a few quick calculations. So, very quickly, A1, by definition, is the product of all elements of the first row. So that's going to be this one right here. So 1 times -1 is -1. B1 is going to be the product of all elements of the first column. So we go like this. So that's going to be 1 times -1 times 1. That should be -1. And we keep going. So I'm going to fill in all calculations very quickly. I've already done this to the side actually. So A2 is 1, B2 is -1, A3 is -1, and B3 is 1. This means if we were to sum up A1, B1, A2, B2, A3, B3, we would get -2, which is clearly not equal to 0. Okay, so interesting. Let's try to go for another example. Let's maybe try to do a 4x4. I'm going to make it a little bit bigger. And likewise, I'm just going to fill this up. Gosh, that's not nice. Like so, and let's just stick in a bunch of minus signs. And similarly, I'm just going to write out all calculations. I've already done this to the side, so should be very quick. But notice that this time we have A1 plus B1 plus A2 plus B2 plus A3, B3, and A4 plus B4 is actually equal to 0. And this can be easily verified. Okay, so for 3x3, we could not get a 0. We got -2, but for 4x4, it is possible to get a 0. Interesting. Interesting indeed. So already we can make maybe a few hints. So we see the 3x3 didn't work, and notice that 3 is odd. But for a 4x4, which did work, we have 4 is even. And this problem, 25 is odd, and we are given that this whole sum cannot be equal to 0. So that's definitely something interesting to think about. So enough with the examples. Let's get on to proving the actual question. So I think we're going to need a new page. So let's write it out. Solution. Here's our solution. So notice we have a very key observation, and that is A1 times A2 times A3 all the way to A24 times A25 is equal to b1 times b2 times b3 all the way to b24 times b25. And that's because all of this is basically just equal to the product of all elements of the matrix. So even though I haven't drawn a 25 by 25 grid, but basically what this left side is saying is if we multiply like this, and this right side is basically saying if we multiply column-wise. So it doesn't really matter if you multiply your numbers through rows or through columns, because in the end, we're just multiplying all numbers together. And since we're asked to prove that the sum is non-zero, let's start off with our contradictory assumption. We're going to assume the opposite. So assume that all of that is actually equal to 0. Now, in general, in math, when you have a bunch of sums like this equal to 0, that's either because you have the case of everything being equal to 0. So it could either be, look like this, 0 plus 0 plus ... plus 0 plus 0. Or another case is because all our numbers in the matrix are either positive 1 or negative 1. What's going on is you most likely have something that goes actually like this. And that's because if we just group the 1 and the negative 1 together, they will cancel and give 0. So we're really just adding a bunch of zeros, just in a different way. And as I said before, I think this is most likely what's going on, because we're not allowed to have zeros in this problem. We just have ones and negative ones. So let's focus on this version. So as I said before, clearly to get a sum of 0, so to cancel, there must be the same number of ones and negative ones. Ones and negative ones. So let's say if among the list of AIs, let's say, so that's A1, A2 through A25. So if among this list there are n negative ones, where n is just an arbitrary number, we don't know n, so I'm just using a variable. So I'm saying that there are n negative ones. What does that mean for the number of negative ones for Bj? This is going to be our key insight. Because we're trying to relate the AI and the Bj to each other. So among the Bj, there are how many negative ones? So I'm just going to leave it as a blank. So I'm just going to do some little work off to the side, because this n might be making things a little confusing right now, and whenever letters are too confusing for you to follow along, just play around with some numbers. So let's see. Let's do a little example. Let's just say we have n equal to 12. That is 12 of the AI are negative ones. Well, if 12 of the AI are negative ones, then this means that there are 12 positive ones from the BJ. And this goes back to the concept over here, right? I always want you to think about this. Always think, if you have a positive one, to cancel, you're going to need a corresponding negative one. So if we have 12 negative ones here, right? Remember, every element is either negative 1 or 1. There's nothing else we can have. So if 12 negative ones from the AI, then we're going to need 12 positive ones from the BJ to cancel them. Because then 13 of the AI are the other possible element, positive ones. So this means 13 of the BJ are negative ones. So to answer our question up here, if among the AI there are n negative ones, then among the BJ there are 25 minus n negative ones. And I hope you see that. I hope you can see it clearly with the example that I gave here. If there are 12 negative ones among the AI, then among the BJ there are actually 13 negative ones. So that number works out for n equals 12, but it can work out for any n. And I encourage you to actually try a different value of n. Like, let's say you can do n equals 20 or n equals 7. Basically, you'll see that this statement always holds because of this very important fact. And I keep underlining this because it's very, very important. That's like the crux of this problem. It's like the main thing that's holding this solution together. So now let's take that fact that we found above and notice that, so we're continuing our solution here. Sorry, I don't want red. N and 25 minus n have different. Do you know what I'm about to say? This is very important. Parities. If n is odd, 25 minus n is even. If n is even, 25 minus n is odd. Okay, what does that mean though? Because it seems like we haven't really been doing much, but the solution is basically almost complete. Do you see it? Because based on this fact, now this means A1 times A2 times A25 and B1 times B2 all the way to B25 have different signs. And so if they have different signs, they cannot be equal. And if this is confusing, always go back to the example above that I did right here with n equals 12. If 12 of the AI are negative ones, then that means 12 AI are negative ones, 13 of them are positive ones. That means their whole product, all 25 of them, is going to be equal to positive 1, because 12 negative ones, when multiplied together, become a positive 1. But over here, with the BJs, it would be a different story. So we have 12 BJs. That product is positive 1 so far, but 13 negative ones, right? For the rest of the BJs means the whole product is going to be equal to negative 1. Since 1 is clearly not equal to negative 1, they have different signs and they cannot be equal. But this is where we have a very big problem, because if you remember at the start of the solution, what did we say? These two are actually supposed to be equal to each other. So the fact that they're not tells us that this assumption does not hold, which means we have found our contradiction, and therefore, if this is untrue, then that means our original statement is true. Okay, I hope you like that one. That one was very nice. And I guess I'll spell it out. Why not? But this contradicts the fact at the start that since I'm so lazy, let's just copy it and just move it around here. Yeah. Okay, this contradicts that. So, therefore, I'm really lazy today, so we're going to do therefore. We're just going to drag everything. Why not? Just copy and paste everything. Just move it around. Therefore, this original statement. Wait, what? Okay, hang on a minute. Thought I copied that one. Should work now. There we go. Let's make it smaller. Okay, and that's the problem done. Let's move on to question number 7. So question number 7 says, on one square of a 5x5 chessboard, which I've already drawn for us, you're welcome, we write -1, and on the other 24 squares, +1. In one move, you may reverse the signs of 1 a by a subsquare with a greater than 1. The goal is to reach +1 on each square, so every square should be +1. So that's 25 squares with +1s in the end after however many moves. So on which squares should this -1 be to reach the goal? As usual, I encourage you to just play around with the problem a bit, which is exactly what I'm going to do actually. So we can even just, let's say, since only one of these squares has a -1, let's just put it here and see what happens. And then the rest are filled with positive ones. And the reason why we say that a has to be greater than 1 is because if you just, change the sign of 1 a by a subsquare, then we can just change this one and then very easily get everything is +1. So that's not what we want. That's too easy. So a possible move, let's say, could look something like this. So let's say after move 1, let's say we focus on this like 2 by 2 subsquare. So that means we're going to change. I don't even know why I wrote that actually. We can just do it here actually. So let's say I want to change all the signs of this subsquare. Then this would turn into, let's be consistent, a positive 1. And then these 3 would be negative. We can go again. Let's say it has to be a square though. So let's say this 3 by 3 subsquare. Now we have to change all of the signs back. So this is a positive 1 again, but now all of these are negative 1s. So that's how the problem works. Okay, so you can, now that we know what it's sort of like, you can try it out on your own, but I'm going to guess that you might not have much success if you followed my example. So if you chose negative 1 to start here, I believe I chose this square as negative 1. If not, well then that's not good, but I believe it was this one. But basically the point is, if you're following along with the video and you chose the same square for negative 1 as I did, I'm willing to bet that after, however many operations you're doing, you probably weren't successful. Because that's the wrong square. That's not what it's supposed to be on. Quick disclaimer. So let's think about how to do this. Now, in fact, I am going to just drop the answer right here on which square it should be, because I know some of you are dying to know, but it's not, the answer is not really important. How we get to the answer is important. So I'm just going to tell you, I think a lot of experienced people with these kinds of problems know that, for a setup like this, if there's only a single negative 1, right? There's only one. What's the most important square in a setup like this? It would honestly be the middle square. If you've seen many problems like this before, that's probably the first thing that came to your mind. If not, that's okay. But more experienced problem solvers probably were thinking of that, and that is the correct answer. So good for you if you had that intuition, and if you did not, that's totally okay. That's why we do this, to build that intuition. But as I said before, who cares about the answer? I care about how you got to the answer. Actually, I kind of want to box that instead. Okay, so let's focus on the why. Now, since we're in the coloring proofs unit, this whole thing has really just been about coloring. We're going to color this board in a very specific way. So watch this, prepare to be amazed. Okay, so basically we've covered 20 squares with the color black, and then this little strip in the middle, these 5 white squares have just been left uncolored, so they're left as white. Why would I do that? Well, now, thanks to this genius coloring scheme, if you notice, every valid A by A subsquare, so that would be any 2 by 2, 3 by 3, 4 by 4, or 5 by 5, every one of these subsquares contains an even, yes, number of black squares. So let's say if I were to choose maybe this 3 by 3 subsquare, you can see we have 6 black squares, 3 white squares. If I chose this 2 by 2, we have 2 black squares, 2 white squares. If I chose this 2 by 2, that's 4 black squares. So basically, we have an even number of black squares every single time. Pretty cool. So let's consider what happens if -1 is on one of these black squares. So if at the start, at our initial position, if the -1 is on a black square, after however many operations, no matter how many moves you make, there will always be an odd number of -1s on the black squares. So if you chose like a -1 here, after however many moves, as I said, you can do 10 moves, 15 moves, 200 moves, doesn't matter, but there will always be an odd number of -1s on the black squares. And the most important question in all of these proofs is always why? Why? Well, remember, every valid a by a subsquare contains an even number of black squares. So we have an even number of black squares, and if -1 is on a black square, when we switch the sign, it becomes a +1. So that's the only sign that gets flipped, and then the other numbers get turned into -1s. So if you don't follow along with that, let's just play around with it a bit. Let's take maybe this one. Right? Let's check out this 2 by 2 subsquare. So if we have a 2 by 2 subsquare, I don't know why this never works for me. I'm like the worst when it comes to this. But if we have this, so I chose something that looks a little like this. Let's say we put our -1 initially here. So I'm just going to do a little bit of simplification. We're just going to do this. So this now represents the grid in its initial position. So let's be organized. Initial position. This is the initial position of the subsquare. If -1 starts on a black square, so let's say after our first move, move 1, we're going to be changing the signs, right? So we got 1, -1, -1, and -1. And remember, because this is the black column, notice we have 1, -1 now, which is odd. We can continue to do this if you need more examples. You really want to get this. So let's say we chose a subsquare like this 3 by 3. And I'm going to do the same thing. So the one we chose looks something like this. And let's say -1 was initially here, which means the rest are 1. So this is our initial position, and then after a move, everything gets flipped. And as we can see in the black column, so that would be this, How many negative ones do we have? Now we have 1, 2, 3, 4, 5, which is odd indeed. So you can keep doing this to really convince yourself, but you'll find that this statement is true. So what does this tell us? This tells us that the negative 1 cannot start on, I don't like the word start actually, let's say cannot be on a black square. So we've already chopped off 20 possibilities. That's nice. So in our coloring scheme here, negative 1 cannot be any one of these black squares, or else we will never get positive 1 on every square, which means we got 5 squares left to consider. Now, an important thing to remember is that the concept of rotation. So, rotations are equal to each other. So, basically, what that means is if you take any coloring scheme of this board and you just, let's say, turn it around, let's say you turn it around 90 degrees, that is still considered the same coloring scheme. And if you have a hard time following through with that logic, the best way I could explain it would be similar to like 6 people. Let's say, let me draw it out, like 6 people. You know how in factorials, if you have, let's say, 6 people sitting around a table, you know that there are originally 6 factorial ways for them to be seated, but then because of the concept of rotation, to fix for overcount, you need to divide by all possible rotations. That would be 6 rotations, and then you're left with 5 factorial. Because rotating a table does not exactly change the actual seating arrangement of the table. So it's a similar idea here. And I'm actually going to add another page. I underestimated how much space we would need for this problem, clearly. Anyways, when we consider all possible rotations, etc., we see negative 1 can only be on the central square. And why is this? Because, let's say, I'm going to take this square. Okay? Let's copy it. Let's say negative 1 was initially on this square, so not the center square. So any white square but the center square. Let's just quickly write in all the numbers as well. So if we were to take this board and let's say we were to rotate by 90 degrees do you know your rotations? What happens, where does this -1 go? If you rotate the board 90 degrees, well, -1 would actually be here. So now it's on a black square actually. So let's write it out. So basically what I'm trying to say is now if we compare these two coloring schemes, so the one on the left and the one on the right, these are considered to be the same. They're considered to be equivalent, which means -1 starting over here would end up on a black square when we rotate it 90 degrees. If -1 were to start here and we rotate it 90 degrees, that means it would end up over here on a black square. If -1 started here, if we rotate it 90 degrees, let's say, it would end up over here. If -1 started over here, we rotate it by 90 degrees, it would end up here. So basically, these four squares, after some form of rotation, sorry, I should do it here actually. These four squares, after some form of rotation, could end up on a black square. The only thing that remains invariant or unchanging would be the central square. It doesn't matter if you rotate it 90 degrees, 180 degrees, 270 degrees, it will always stay on a white square because that is the beauty of a central square. It doesn't move under rotation. So that is why -1 can only start on the central square, the center square. Very nice. I would say that was probably the trickiest one of the night, only because of this coloring scheme. And I'm going to repeat this at the end of the video as well, but you might be wondering, how do we even think of this coloring scheme? Because that is bananas. Like, of course, if you think of this, then it greatly simplifies the solution and you can answer the problem pretty quickly. But if you can't think of that, then you might be a little confused, right? And you're spinning your wheels. And the best answer I have to say to that is just to get a lot of experience, which is what we're gaining tonight. You need to see many different types of coloring schemes. So we've already seen, basic chessboards. We've seen coloring things diagonally, right, with numbers. And then now we're seeing coloring, by columns now. So there's many different types, and that's the goal of this video, just to show many different types of coloring. So don't just get fixated on one method. So what did we learn from this problem? We learned that we can color through columns, and that should help with one of the homework problems that you'll see later. But we also learned about the concept of rotation, which will pop up in the next question as well. So let's take a look at it. Without wasting any time, here is your next problem. Okay, everybody, sorry, but quick little note. As I was rewatching the video I made, I realized that the screen recording for question number 8 was actually not working. So I actually did the whole question, but the screen did not capture it, unfortunately. So it was super laggy and unbearable. It was really hard to watch. So I decided that I'm just going to quickly go over the solution now. So once again, I apologize that we are not going over this together live, but I will do my best to explain it right now. So in the question document, you saw that this 12 by 12 chessboard was originally blank, and for this solution, what we did is we colored it once again diagonally like this. So you can see 1, 2, 3. 1, 2, 3, so on and so forth, just along this entire board. So this is another example of a diagonal coloring problem. And you can count if you want, but I've already done it for you. There are 48 1s, 48 2s, and 48 3s when you color it in this fashion. So basically each number appears 48 times, and any 1x3 tile will cover exactly one of each number regardless of position or orientation. And you can see this easily. You just play around, place them on the board, whether it's like this, or like this, or like this, or like this, and maybe like this. You can see each time 1 1, 1 2, and 1 3 gets covered. This means that if we remove 3 squares, we need to remove 1 1, 1 2, and 1 3 to tile successfully. So that's how we go from 48 to 47 of each. And in our problem, we are given that 3 of the 4 corner squares are removed. So right away, we can already tell that we cannot remove these 2 corners, because then we would be removing 2 3s, which is not allowed. So that's this entire portion right over here. This means the upper left and the bottom right corners cannot be removed. They cannot both be removed. And from the last problem, we need to consider rotations as well, because rotations of the board are considered to be equivalent positions. We find that rotating the board 90 degrees shows that the lower left and the upper right corners cannot be removed as well, because if we were to take this board, rotate it 90 degrees, this 3 would move over here, and this 3 would move over here. So now we would have the 3 here and the 3 here, so the lower left and the upper right corners cannot be removed as well. So now we are in a situation where we cannot remove these 2 corners and we cannot remove these 2 corners. However, in our problem, we need to remove 3 of the 4 corner squares. But do you see the problem? Because if we are to remove 3 of the 4 corner squares, it will involve 1 opposite pair. For instance, if, let's say, we remove this 3 and we try to remove this 2 as well, no matter which one we choose, whether it's this one or this one, this next corner square that gets removed, we are going to have a pair that is completely opposite to each other, which is not what we want. So as I said before, if we remove these 2, if we remove this as the 3rd square, then we have removed the upper left and the bottom right, which is not allowed. Again, if we instead chose to remove this one, now we have removed the lower left and the upper right, which is also not allowed. So basically, no matter how we remove the 3 corner squares, it will always result in 2 opposite corners being removed, which is why this will never work. So in conclusion, it is not possible to cover the remaining area with 47 1x3 tiles. And that's question 8 done. So once again, I apologize for not doing this live with you. I would have loved to do all of this live and explain the steps each way, but hopefully this is good enough, and I hope you understood that. So let's get on to question 9. let's talk about bricks and boxes. So that would be 3 dimensions, because I want you to realize that the same techniques can be used in 3D problems as well. So that's great. That's the great thing about this coloring principle. We have applications in 3D as well. So we're not just limited to chessboards and 2D, the 2D world. So let's do this. This is the final question of the night. So if you've stuck around this long, first of all, what are you doing? But like, why would you watch a video made by me this long? But I'm guessing you like to be here anyways. If you stuck this long, congratulations. This is the final problem. So let's finish strong. This is a good one. I really like this one, by the way. It's a simple question. It says, can you pack 53 bricks of dimensions 1 by 1 by 4 into a 6 by 6 by 6 box? The faces of the bricks are parallel to the faces of the box. So we're not going to have, any of this like a tilt. Oh, that was horrible. But like basically there's no like tilting going on. Okay? They're like stacked pretty neatly. And we have another light bulb here because it's very important. This concept shows up in 3D geometry in general as well, because I'm like everyone else. I basically find it a lot simpler to work in 2D, which is why, and in fact everyone does, like there's not a single person who would rather work in 3D than 2D, because 2D is just so much more simpler. I want you to turn a 3D problem into a 2D problem. So that's your challenge. Your challenge is to turn this 3D problem into a 2D problem and then color it in such a way as if you are in 2D space, basically. What we've been doing all night long to help you with this problem. So for a question like this, it's very important to have a good sense of numbers as well. Because if your general feel and intuitive sense of numbers is strong, you can get some very creative insights. Stuff that seems like out of this world, That's why it's very important. So this 6 by 6 by 6 cube, let's see what I mean, okay? Consists of 27 subcubes of dimensions 2 by 2 by 2. And this can easily be verified. This is just basically a volume. So each cube has dimension 2 by 2 by 2. So that would be 8. And then since there's 27 copies of them, 8 times 27 is 216, which is exactly 6 times 6 times 6. So basically everything fits nice and compactly. Great. And if you have trouble seeing this, I'm actually going to do my best to draw it out for you. So I'm not going to draw all 27 subcubes, but I think I'll go ahead and draw the bottom layer, the base layer that I want you to see. Okay? So this is what I want you to see. In case you can't see it, you're probably just like what is he talking about? Well, then let's do it. Let's make things more clear for the student. Okay, so it's not perfect, but I did the best I could. So I hope you can see this clearly. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 2 by 2 by 2 cubes, and this can be considered to be sort of like the bottom layer. So you can imagine if we had 3 copies of this stacked vertically against each other, it would fill up this entire cube, the remainder of this cube. Now that we got that out of the way, in fact, I'm going to, in case you can't see, let's really make it clear. Four, 5, let's number them. 6, 7, 8, 9. And since there's 3 layers, we're going to have 27 subcubes. Great. So now it's time to do some coloring. So we're going to color them alternately. Black and white, so good old 2 colors, sorry. As a chessboard. And now here's where the concept of turn a 3D problem into a 2D problem comes in. Because I do not want to draw cubes, I would rather draw squares. So let's do that. This will never get old. Like, I will never be able to do it. Again, it didn't work. Oh my gosh. Can it work this time? That's not a square. God, you guys are just watching me struggle. Finally. Okay. So I am going to copy and paste this many times. I'm going to need 27 of these. So I'll be back. I'll just do this really quickly. Okay, and we are back. So I am going to now add a few lines to represent the different levels. So let's consider this one to be the bottom section. This one will be the middle section, and this one will be the top section. So basically every single subcube like this, right, has now been transformed into just a square, just for simplification, right? We like to simplify things, but just know that this is not actually a square, this is really a cube. Now, I said we're going to color them alternately, so it's very important that we stay organized with this. So let's start off with, if I just call this black, then this would be white, black, white, black, white, black, white, black. Now because this cube is directly above this cube, remember these are layers, so this cube is on top of this cube is on top of this cube is on top of this cube, so on and so forth. So if I went like this, then the cube above it we're going to color white, and we continue black, white, black, white, black, white, black, white. So now I've gone sort of like this direction, and since this cube is directly above this cube, now we're going to color that black, and actually it's the exact same color scheme as the bottom layer. So we're just going to fill this in, work our way around, We really want to make sure we're doing this properly. Okay. And once again, I greatly underestimated how much space I need. So let's just add one more page like that. Okay. So let's count. How many white subcubes do we have? We have 4, 5, and another copy of 4 on top. So 4, 5, and 4. That should be 4, 5, and 4. That's 13. So we have 13 white subcubes, which means the volume of this, the number of individual squares that they cover. Remember, each cube is 2 by 2 by 2, so we really have 104 white unit cubes. Unit cubes are 1 by 1 by 1. Great. Since we have 13 white subcubes, we have 14 black, because remember we have 27 in total. And the amount of unit cubes that they cover is 112. And notice that any 1 by 1 by 4 brick uses up exactly 2 black and 2 white. Unit cubes. If you're struggling to see this, so remember, each subcube is measured 2 by 2 by 2, so that would be 2 directions, 2 units in this direction, 2 units in this direction, and 2 units back, even though you can't see the back. But it's 2 by 2 by 2, so if we were to take a 1 by 1 by 4 brick and place it horizontally, since 2 plus 2 is 4, it would cover like this. And if we were to place it vertically, remember this white subcube is above this black subcube, so if you were to place, the 1 by 4, the 1 by 1 by 4 brick upwards, it would be 2 black squares and 2 white squares, like so. And since we can't tilt, we've covered all cases. So we can either be horizontal, like this, or we can be vertical, like this. Okay? Great, that's all we're saying. This means that if we have, let's go back, so we have 53 bricks of dimensions 1 by 1 by 4. Sorry, I should be black, so this means 53 1 by 1 by 4 bricks equals 106 white cubes used up. But we got a big problem, because how many white cubes do we have? 104, so we don't have enough. We only have And let's write down my favorite word of the day, contradiction, because that's basically what we've been doing all day. This is all just proof by contradiction. And of course, I just happened to choose 13 white and 14 black, but again, without loss of generality, it goes both ways. It could have very easily been 13 black subcubes and 14 white subcubes, and then in that case, we would need 106 black cubes, but we only have 104 black cubes. So it's the same logic, works for both colors either way. And yeah, that's it. I hope you can see that this coloring theory has many applications, even to a problem like this. I think that's a nice one to end on. Hopefully this was kind of clear. Again, it might be a little confusing because I flatten them into squares, but hopefully you could follow that along. And now, with that being said, guess what? Class is not over. Well, I mean it is, but your learning is not over because you have 3 questions. I had more, but I think 3 is good enough. Yeah, because there's a lot more that we can do, and it's very fun. But this is kind of just like a introduction to it. So here are your 3 questions. Have fun with it, and this little star over here is not a coincidence on number 3. It's not a bug or a glitch. I put that little icon there because that means it's hard. It's hard. And a lot of times I actually couldn't even do it myself. So yeah. This one, yeah, I could not do myself. So hopefully you can have fun with that. So I'm just going to go through them very quickly. I'm not going to show you how to do it in the document I attach. By the way, I will be attaching documents. So there's a document that is clean. It only has problems, so you can add your own notes. You can follow along with this video and add your own notes. But then there will be a document with, all of this detailed solutions. I'll export it, and then I'll also include a document with solutions to homework, because you probably want to know how to do it. So yeah, don't worry about that. So I'm not going to show you how to do it right now. Of course, that's for you to do, but feel free to try this out yourself and then compare it to what I show. So I'm going to just talk through them very briefly. Number 1, you should get it. No offense, but if you can't, that's totally fine. But the reason I say you should get it is because we pretty much covered it in the video. Number 2 is a little bit more tricky, I would say, but I think my big hint to you for this question is to think back to question number 8. Remember how we colored it in columns like this? I want you to do something very similar for this beetle problem. And well, you'll see what I mean. Yeah, I don't want to say too much. Okay, and number 3, yeah, good luck with that. Basically, that's all I'll say. Just good luck. But if you want me to explain it a bit so that you know the rules, basically we got these 5 heavy boxes. We can't rip them apart and lift them and then carry them. We have to basically just roll them on its edge, right? Like that. So we start in this position, we end in this position, and they're asking for which box here, which one of these boxes was originally this one. So at the very center, after lots of maneuvering, lots of rolling around, which one of these 5 was here? And I guess I'll be nice. I'll give you a little hint. It is actually not this one. I know this one is standing out because it's a little weird. It's on its side, right? Every other T is like standing up, and this one is to the right, but no, it is not this one actually. So you got four more guesses. Okay? So have fun with that. And yes, in case anybody was curious, not all of these problems, but almost all of these problems were from Arthur Engel's Problem Solving Strategies book. If you recognize these, yeah, that's where a lot of them come from. So it's a pretty good book. I recommend it. Pretty challenging book though, and I guess my only issue with it was that, seeing as it's a Springer book, a lot of times the solutions just say, they're really short. They're like, maybe like 5-6 sentences at most. And a lot of solutions are like, oh, exercise is left for a reader. It's pretty trivial, or they just state a fact that seems so obvious to the reader, but it wasn't obvious to me. So that's why, like for instance, a lot of these problems I had to really think it through and explain it in greater detail, because I am not that smart, so I was struggling to understand their solution quite a bit. So hopefully this made things easier for you. And another great thing is I basically compiled it all into one area. These questions are all really similar to each other. The actual book has I think 30-40 problems, so there's a lot more applications you can do with culling problems, but for now I think 12 problems should be good enough. So that's 9 in the document and 3 in the homework. So have fun with that. I'm going to stop talking right now because I'm talking too much. And yep, that concludes this first video on the 22 circles math channel. So that's not 20 circles. This is 22 circles. And on this channel, we'll just basically be doing harder stuff, basically. So if you found this a little too challenging, I think you should just go to 20 circles. That one will have more beginner-friendly lessons, but this one is going to have some pretty challenging stuff. It's mainly for the math enthusiast, I guess I would say. Math enthusiast, math major, but honestly, anyone is welcome. So that concludes coloring. Yep, that concludes coloring. Let's go back to the start. So this has been coloring proofs. I hope you enjoyed the video, and I will see you next time. Goodbye.